Hi everyone and welcome to our webinar entitled Safeguard Your Embedded Linux Device with Secure Boot hosted by Toradex. While we wait for more people to join, here are some important notes for the webinar. At the end of the session, we will have a Q&A. So if you have questions during the webinar, feel free to type into the chat box. We will address them in the end. And if you encounter any technical issues such as audio problem, please use the same chat box to let us know and we will assist you as soon as possible. Lastly, this webinar is being recorded and will be made available on demand on YouTube in about a week. And with that, let's get started. So let's switch slides. My name is Stefano Viola, and I am the Torizon Group Engineer Manager and Software Architect here at Toradex. Joining me today is my colleague Drew Mosley, Technical Solution Architect. Drew will join us later in the webinar to present a demo. In this demo, he will guide you through the setup, build, and boot process of a secure boot image, followed by some final consideration. Okay. So, key takeaways of this webinar: learn all about secure boot, explore how it simplifies compliance with cybersecurity regulation, such as the European Cyber Resilience Act, understand how Toradex and in particular Torizon make it easy to start securing your devices, and learn how to reliably and securely update the Bootloader OS application and other components even in a secure boot enabled device. Moving forward. So, why you need secure boot? I decided to pick two most important reasons. First, you need it for security reasons. Let's say that you want to guarantee end customer safety and security, so you decide to add secure boot to your product. Second, probably the most important reason for most of you, you need for compliance. There are many regulations around the world where secure boot is a requirement, and most important one is for sure the new European Cyber Resilience Act. In general, most all those security regulations state that the embedded device must guarantee the, let's say that the booting software image is trusted and has not been tampered with. Just a quick recap about the Cyber Resilience Act. So it's a new regulation, a new European regulation covering all digital products, except for products already covered by stricter regulation like medical and automotive and military, but basically all digital products. Entered into force the last December 2024, so now it's a reality. Thought most provisions won't take full effect until December 2027. And secure boot will be necessary for Cyber Resilience Act compliance because of the following provision, as you can see here highlighted. So products shall protect the integrity, commands, program, configuration against any manipulation or modification not authorized by the user. And consider that secure boot is only one aspect of this Cyber Resilience Act. I really invite you to see, as you can see here, there are some reference. I invite you to watch our dedicated webinar on the Cyber Resilience Act that we go really deep in detail of what it is and even how Toradex can help you to achieve this complex regulation. So let's start with the first poll here. Okay, you should see now the poll on the screen. Have you used secure boot in a design? So yes, but only on x86, yes on ARM, no, I never did it. Let's just take 20 seconds to collect some answer from you. Let's see, let's wait other 10 seconds. Still someone voting. Okay, let's close it now. Let me share also the results. So it seems that most of you never implemented secure boot. But yeah, there is even a good percentage, almost 22% that did on ARM, just few on x86. I mean, this is pretty reasonable and is what I was expecting. Okay, let's go ahead with the presentation now. So, what is secure boot? So, if I should summarize the concept with a single sentence, I think the best way to describe secure boot is that it's a system boot process capable of verifying the authenticity and integrity of all the software boot artifacts. Authenticity means that the system must guarantee that the image come from a verified trusted source. In more simple word, we'll check if the image that is booting is your image. Instead, the integrity will guarantee that the image has not been tampered with in any way. But you may have came across terms like verified boot, measured boot, chain of trust. These all refer to the same core ideas. Locking down your device and assure it only uses trusted and secure software images. Now you might wonder about encryption, TPM, because usually are argument associated to secure boot. And I want to take a few seconds to clarify it. So encryption, secure boot does not require encryption. Encryption is typically implemented to protect data, but is not a prerequisite for secure boot. What I want to say is not really needed to implement authenticity and integrity check. Similar for the TPM. TPM is Trusted Platform Module. For those that don't know what it is, it's an acronym for that. It's not needed in any embedded device to implement, let's say, secure boot. For secure boot, usually chip vendor like NXP and Texas Instruments, I just provided these two examples here, already provide all the necessary hardware feature to implement the process without requiring any usage of the TPM. I mentioned here that, for example, for the iMix processor, we have the advanced hub and hub based on which processor you are using. On the IM62, IM69, there is this HSM. Let's move on. So now, let's see how secure boot works. What you can see here in the screen, it's a simplified representation of a typical embedded system boot process. So we have the SoC ROM code that will load the bootloader. Then the bootloader will load the Linux kernel, init RAM disk, device tree, and so on. And a system that supports secure boot will be able to verify the integrity and authenticity of each component of the software stack. In general, each component is in charge to verify the next one. And that's why it's called the chain of trust. As you noticed, in almost every block, there is a public key. For example, if you see in SoC ROM code, there is a public key 1, in the bootloader is public key 2, and so on. This means that your building system or your tooling must be able to sign every component with a private key during the build phase, but then attach the public key to the component itself to allow the system to perform the authenticity check during the boot phase. About the SoC boot ROM code, the situation is a bit different because there is not a software. It's something that is it's a ROM code, is fixed in the chip, in the processor. So it's slightly different, but be aware that enabling this feature in the SoC, it's one-time operation. The process to add the public key in the SoC, it's one-time operation, and even the operation to actually enable secure boot. So you really need to be careful. And this process is usually called the fusing process. Yep. Let's now go to the next. Now let's try to analyze how it works, this boot process. Now, let's take a look of these first two blocks here. So we have the SOC and the bootloader. As I said, to enable secure boot, you need to fuse your key in the SOC, and this action is hardware specific. This means that every chip vendor have his way to perform this action. But in all the cases, it's a one-time operation. So you need to be really careful with it. When the key is fused and secure boot is enabled, the SOC ROM code will check if the flashed bootloader is signed with the proper key and will execute it only if it matches. This step is basically the root of the trust of the entire system of our embedded devices. So if doesn't match this check, the system will not boot, will just be bricked. Moving forward, let's assume that the first check go well. So now the bootloader is up and running, and we are talking about U-boot. So now what happened? The U-boot bootloader, in case of a secure boot image build, will contain the public key of the entire fit image. In the bootloader device tree, usually is shipped this public key, and we'll use it to perform the check before loading and executing the fit image. The fit image, for those who know, is a single image that contains inside the Linux kernel, the init RAM disk, device tree, and so on. And during the loading of this image, the system will also perform the integrity check, understand if every component was tampered, let's say. So it's, as we said at the beginning, we do both integrity and authenticity check. Next, kind of obvious, the initramfs in this case is the subject that includes the public key and will perform the authenticity check before to start the loading process of the root file system. If every check is positive, the system will be able to boot. Here, the root file system is basically where you have your system. Now, the system used to perform the integrity check of the root file system can change based on your, let's say, operating system. For Torizon OS, as you can see down in the notes here, for Torizon OS, we use compose-fs plus fsverity to perform the integrity check that we need. It's a kind of special case because in Torizon, we only have one partition, and this partition must be able even to receive updates. It's slightly different than a system that have two partitions. But there are other systems, for example, more traditional, that use dmverity, that basically make the whole partition read-only, and and then with dmverity you can do the transfer integrity check and so on. So in this webinar, I don't have really time to explain in detail how it works, compose-fs plus fsverity compared with dmverity. It's a pretty complex topic, but since are all standard tools, I suggest you to look into the reference link that we added here in the slide, and you will find all, let's say, all the information. So at this point, the system is fully booted. But now let's take a look to an animation that we prepared here to see how the whole chain of trust and boot process works. Okay, so as you can see here, we start from a point where we have a device. In this case, it's one of our device, Toradex device. It's already flashed, it's already fused, it's already closed. So what happened? So as we explained, as I just explained a moment ago, the first subject that will start the process is the boot ROM code. So the boot ROM code will do the check to understand if the fused key match with the key the key that was used to sign the bootloader. Then, if this match go well, next step is the bootloader will check the key that he has inside to the key that was used to sign the Linux kernel. I mean, in this case, it's fit image. Then last check will be the initramfs. As I said, we'll check if the root file system is the correct one. And that's it. We have a successful boot. But now, what happens if a malicious guy here, represented by this guy with the red t-shirt, will build his own bootloader with an exploit inside and will flash it? Because secure boot is not that protect you to flash artifacts. People can still continue flashing artifacts. So let's imagine he creates this malicious bootloader, signed of course with his private key, because he don't have the key that you used the private key that you used to build your image. So what happens is that when the malicious guy will flash the bootloader in the device, of course, the boot ROM will just recognize that there is no match for the key, and the boot process will just stop. So which attacks are prevented by secure boot? Now that you should know how it works. Any modification of those components that you see in the list are prevented. So no one can modify bootloader, of course, except the one that has the private key to do it. So no one will be able to modify the bootloader, his environment, or whatever other script user for the boot. The same for the kernel, device tree, or overlays, and every file of the system included in the root file system. But which attack are not prevented by secure boot? You must keep in mind that secure boot is just about protecting the boot process. So when the boot is finalized, I mean the initramfs will do the last check with root file system, and root file system boot, secure boot is done. Secure boot will not do anything else. So this means that whatever runtime attacks could be an issue. Let's do a real example. If, for example, you don't take care about how you configure your device and you leave an open SSH with the password 1234, people will be able to access your device and even install arbitrary code on the system, even if it's read-only. But I think you know that you can write things in RAM. You can have even a temporary RAM partition. Will be complex, do something that will be permanent, but at least could be that someone can do a runtime attack, because the secure boot does not protect you against this. Of course, if someone replaces the SOC, is an issue. I mean, very complex to do, but it's something that someone could do and avoid, let's say, the secure boot part. And also, let me clarify, because I also said this before, secure boot does not protect you against the flash memory dump. So if you have some secrets on your device, whatever secrets, that could be calibration file or whatever, if someone just take your device, could do a memory flash dump and read everything clearly. What I want to highlight here, that there is no risk for the secure boot part, because even if people will be able to read your public key, it's the public key. So they cannot do anything with the public key. To generate a valid image to be flashed and executed in your secured system will need the private key, but the private key, it's something that you store in your company very carefully. So on the system, there is nothing sensible from the secure boot point of view. But on the data point of view, could be that you have other needs and you will need, for example, an encrypted partition. So just to recap, is secure boot all I need? Of course not. But of course not for every reason, for compliance, but even from security point of view. Security is never done at the end. Every day can come something new. So we must be able to address newer challenge, and even pretty fast. it's a mindset, it's a process as I wrote here. So secure boot is just one security measure. So then here I listed a few, but there are many other things that you should consider. For example, you should consider do a proper credential management, key management in your company. You probably should consider to do some secure coding, to adopt some secure coding practice if you don't have it. Do regular patching, updates, monitoring of the CV vulnerabilities, because as I said, there is the runtime part that is not, let's say, covered by secure boot. So you need to be careful if there are some exploits that people could use. So, but now let's just say how Torizon can help with this. And this is exactly the reason why we decided to create Torizon and all the suite. Torizon is designed to help you to implement not only secure boot, because yeah, probably you already know, we have secure boot out of the box, especially for all our hardware portfolio, but also to address all the key security aspects of your embedded devices. It's built with the security at its core. Torizon make it really easy to build a secure boot image and establish a robust chain of trust. Basically, everything that I explained before is really easy to do. You don't need to code anything, will be just available. Then Drew will actually show you this. With Torizon, you can even generate a very precise and reliable software bill of material. That, just a note, this will be needed for cyber resilient acts. You could leverage vulnerability monitoring to stay informed on potential risk, because this is something that we do daily. Receive timely security patches to address vulnerability quickly. Utilize a robust over-the-air update system inspired by the automotive industries. And probably most of you already know our OTA system is based on a standard called Aptain, which is specifically designed to protect against sophisticated state-sponsored attacks. As you can see here in the slide, we provide a full stack of we provide a full software stack, but also a very rich feature set. So in Torizon, you can get not only an OTA system, but also device monitoring, a very nice and secure remote access feature, secure offline updates that are needed, subsystem update that can be used to target updates for external microcontroller, FPGA, and so on. So we provide also a very nice web UI with standard RESTful API for people that decide to eventually re-implement it or to automate some of the actions that allow really easily manage remote your device. Talking a bit more about the OS, because it's where secure boot, it's implemented along with other security feature. I want to highlight that Torizon OS is Yocto. It's just our branded name for this Yocto setup, but it's 100% compatible with Yocto. And in this slide, I tried really to clarify this, because as you can see, we use a standard open embedded layer that we can refer as the standard Yocto. Then, of course, there could be some chip vendor layer. Here, for example, is present everything related to our hardware in case of Toradex, but in case of whatever third-party hardware, will be here the definition of the machine that you want to build. And then what we have is that we develop and maintain two additional layers. Meta Toradex Torizon, that to simplify, it's the meta layer where we include all the recipes for the OTA agent, called actualizer, container engine, OS tree, device monitoring agent, FluentBit, and so on. And then we have a specialized, let's say, meta layer called Meta Toradex Security, where we implemented all the security features. Here you can find the secure boot. Here you can find even an implementation to easily use TPM, for example. You can even find something about OPT and soft TPM, FTPM. Basically, we have an example where you can actually build a software version of TPM using the trusted execution environment provided by ARM. And this can be used to implement an encrypted partition. And about the encrypted partition, what also we have here, really ready out of the box, that you could have an example. Of course, if you enable it, the system will like build for you an extra partition and will use to store each secret, because when you have an encrypted partition, you need to have a place where store the secret to be able to read and write. Using OPT with soft TPM, using real TPM, or using even CAM in case you are using, for example, NXP. I think it's very, very cool meta layer. And I invite you, for the more technical guy here present in this webinar, to look to our repository. All our development happen publicly. You can find here the repository on the GitHub. Okay. Last but not least, Torizon is open source. So there is no lock-in mechanism. You can stay flexible if you adopt it. There are no secrets. You can still, if you have the needs, you can still modify the software based on your needs. You can download all our layer. There is no single bit that is closed source on the device side. Then we have really a huge community that can really help you to achieve what you want. And also, let me highlight that we are hardware agnostic. So you can use, let's say, Torizon on our hardware, and of course, you will get the best user experience. All the features on our hardware are available out of the box. But of course, no one prevents you to use a Raspberry Pi or whatever other chip, even x86, etc. This is pretty useful when you have, for example, cases where there is a mixed fleet, where you have some devices that are x86, some of devices that are Toradex, etc. You can always use Torizon to manage all of them. Okay, let's do the second poll. You should be able to see now. Are you planning to implement secure boot? Yes, in the next 6 months. Yes, but in the next 2 years. No, or I'm still undecided. Let's wait a bit, the usual, time to collect all the answer. Still people voting. Interesting. Let's just wait a few seconds. Okay, let's close it. Let me share. Okay, it seems that most of you, 50%, I mean, more than 47, let's say, will do it in the next 2 years. But that's really good that 44% of you will do it in the next 6 months. This is really, really, really interesting. So I think that in this case, really, Torizon is something that could help you. Okay, let's remove the poll and let's go to the next. Okay, so now let's move to the demo. So I will turn it over to Drew that will present it, and we will see again at the end with the Q&A session.
Yeah, good afternoon, good evening, good morning. Thank you for joining. So yeah, real briefly, just to cover what we're going to show here in the demo. I'm not actually generating a new set of keys or certs, but I will show you where I have done that. This is very SOC specific. In this case, I'm demoing on an NXP-based module, so I followed the instructions from NXP to generate this. Then we built the Torizon OS using a Yocto build, and as part of that, we inject the keys into the build image. It gets signed as part of that, and some instructions to close the device are generated. We'll take a look at that. Flash with Easy Installer, I'm not actually going to do that on screen because I've already done it, and then I've also used U-boot to manually fuse the keys, but the one step that I have not done is closing the device, because this is a test demo device. I want to make sure, obviously, that that I can continue to boot unsigned images. So that final step of closing the device is really expected to be done in production when you're ready to go into final production. So moving on, let's pop out of full screen mode. This is the GitHub page for the Toradex security layer that Stefano mentioned. And this layer is applied along with Toradex Torizon to generate the secure boot signed images. This layer also supports secure boot and other security features for the Toradex BSP reference images. So if you're not working with Toradex, you can actually go in here as well. But we'll get into some of the differences in the functionality as we move further on. But you see here, secure boot, obviously that's what we're here talking about today. This layer also supports full disk encryption, as well as opt-t and things like the firmware TPM and things like that. And this layer is undergoing active development. So if you have any questions, issues with this, right? Most of the activity related to this layer is happening here as standard GitHub issues and pull requests. So feel free to jump in there, report issues. If you have contributions you'd like to make, we take pull requests. We'd be happy to see that. I did want to jump over here real quick to look at the docs specifically for the IMX-based platform. So there's a README for IMX. There's also a README for the TIAM family, and all the instructions are here. You get the code signing tool from NXP. There's some documentation you get from them that show how to set that up. And then there's some variables that you set in your local.conf when you're doing the build. For the most part, the defaults are set so that you don't really need to change anything. Simply setting the TDX IMX have enable is usually enough, and then obviously you have to tell it where the keys are that you've generated. And then at the end, you will get this fusecommands.txt file, and so this is one example. These are U-boot commands that you have to invoke. Today, it's a manual step. It's something we're looking at implementing automation for. But like Stefano said, this is a one-time operation. This first block of steps here is actually fusing the key into the SOC. And this is what I have done on mine. This last block here is actually closing the device. So this is when you are putting the device into the mode that it will never boot an unsigned image. So you want to be real careful when doing that, because obviously once you've done that, you are very limited in the things you can run on the device. So we can take a look here. So what I've done is I've got a Verdin mini board, and I need to power it on here, and it is already installed with a secure boot enabled image. And so what I then did is I did another build with an image that is signed with a different key. So this kind of represents the hacker mode. Oh, and since I'm not fast enough on the keyboard, I was unable to show what I wanted to see. So like I say, I have not closed this device, so it is still able to boot the unsigned image. But if we break into U-boot here, you see some information in the U-boot logs about authenticating the image. It does say the fuse is not enabled. This is what I was referring to when I said it wasn't closed. So in this case, if we look at the hab status command, we see all these events coming through, which are basically a sign that we had a hab failure. So since my bootloader in this case is not signed with the key that corresponds to the key that I programmed into the SOC, we get this boot failure. So now what I'm going to do is I'm going to quickly reflash this board with one that is signed, so we can take a look at a boot issue when the kernel is updated. So I will just real quick kick off this. And then while this is happening, we'll take a look at a couple other things. Okay, so my install is happening. So now if we come over here, this is actually my build system. In cooking show fashion, I have multiple builds here. So I have one build that has no secure boot enabled, one with the what I'm calling black hat. These are the keys that are not associated with the device, and then white hat, of course, are the keys that are associated with the device. So in my case, if we take a look at, we'll just take a look here. So, no, not that file. I want to look at my auto.conf file because that's where I put my settings. So these are all the settings that I set up to enable secure boot. So, you know, I inherit the TDX sign, which is the first step. I guess that one that I mentioned is done automatically when you inherit TDX sign, and then I simply tell it where the directory is that has the keys. And so in this directory is where I have the keys that have been checked out from that device, and then the steps follow in the NXP documentation were followed to actually create those keys. And then when I was setting this up, I used a non-default algorithm. So in my case, I actually have to explicitly specify which algorithm was used when I generated the keys. But if you're using the defaults, you wouldn't need that extra setup. So once that's done, it really is just a standard Yocto build, following our standard Yocto build instructions. The output is a standard TESI file. So if we take a look at you know, we've got our standard TESI file that I can deploy using our Toradex easy installer. And then once that's done, which is actually what's happening in the background here, I'm keeping an eye on it, then my device will have been flashed. One note, and there actually is a question in the question stop this, the Toradex easy installer obviously is not signed with your private key. So it's the ability to actually launch the easy installer once you have completely closed the device is you're unable to do that. So you do need to take other precautions and make sure you have other arrangements to be able to actually keep your device updated, and you know, things like the Torizon OTA update system certainly can help with that. So just another second here, and my device will be booted, and we can take a look at a proper boot, and then we can do quickly overwrite the kernel and see an actual boot failure. Okay, I think we are almost done flashing my board. Somebody in the questions is asking about how I get access to a shell prompt in Chrome. Yes, I use the Chrome SSH extension and just SSH to my board. I find it very handy for giving these kind of demos. Okay, so now we are up and running with a properly signed image. So if we move back over to the terminal window here and launch my board, we should see in this case, missed it again, but we are getting a successful boot. So I'll wait, and we see that the system has started, no issues. And then once that finishes, what I'm going to do is cheat a little bit, and I'm going to overwrite the kernel just using an SCP command. Okay, so now that my board is up and running, let's play the part of a hacker, and I am going to overwrite the kernel in the device here with this big long SCP command that I obviously prepared ahead of time. So now I have a kernel that is signed, but not with the right key. I log in. So we'll go ahead and let the system reboot, and we will see when the device comes up, we see, again, it's trying to authenticate. Now it actually loads the kernel, but it is unable to verify the signature, give some additional warnings because I'm not in closed state. and it's actually unable to boot this particular kernel image. In this case, if I look at that hab status command again, since the bootloader is now signed properly, we do see that we don't have any hab events. So in this case, this was the case where the bad actor is overwriting the kernel. So we got just a few minutes left here. I'm going to quickly run through these last things, and then we do want to do some Q&A. Just briefly to talk about the support level for Secure Boot on Torizon. You see the overall view here. Everything in green is supported as of today. We've got 2 items in progress that have to do with migrating between the various levels of support for Secure Boot for devices that are in the field. So where you see BCOT, that's the basic chain of trust. ECOT is enhanced chain of trust, and FCOT is the full chain of trust. And you know, the main thing that we don't have support for today is protection of those container images and the updates to the containers. That is planned work that will be done in the Torizon 7 product line. And then obviously the in-field migration is work in progress that we want to allow you to get your devices updated in the field. If you are using just the BSP reference image, that's fully supported and feature complete at the moment. There are no additional plans to do anything here. Just beware that if you do use this, obviously there's no update system built in there, so that does make your life, give you a lot more work that you're going to have to do. And just in general, talking about integrity protection in the various images that are provided and supported by Torizon, you can kind of see the overall workflow here. You know, if you're using either our BSP reference images or our Torizon Yocto minimal image, obviously there's no Docker protection. You don't get install time protection with the BSP reference image because there is no update system built in, similarly on the root file system, but you do get that runtime protection that Stefano outlined at the top of the webinar. If you're dealing with Torizon OS, whether the Yocto minimal image or the Docker related image, you do get protection of both the bootloader and root file system and the kernel and those kind of components as well, both at you know, install update time as well as runtime. And then of course the Docker based applications, you are protected at install time, but you are not yet protected at runtime as was shown on the previous slide. So the integrity protection provided by the Secure Boot as implemented here, you see the full details for the various reference images. And one last note here, you know, Secure Boot provides protection of the installed images. You still, when you're dealing with an update system, need to deal with update security, right? Both systems will provide authenticity and integrity guarantees, but they're not the same. They complement each other and are both necessary. You know, without Secure Boot, in theory, you could just completely overwrite the entire block storage of the device and take over a device. But without proper software update security, you could do something similar at the update layer. So all of that to say, you really need to think about, you know, both the Secure Boot as well as the update security mechanisms. You know, they do use different keys. They're not necessarily related, but they do use similar underlying technologies. And as far as Torizon Cloud compatibility, one of the primary goals of the team is to, when implementing Secure Boot, was not to break any platform features. So basically anything that you could update in a non-Secure Boot enabled device, whether it's you know, bootloaders or subsystems or anything, that will continue to work when you're dealing with devices that are Secure Boot enabled. And just a final note on the tooling, what we looked at in the demo and in the GitHub, both BSP and Torizon use the same basic mechanism. There's obviously some minor implementation differences, but today you do have to do a Yocto build if you want to enable Secure Boot in your Torizon builds. We are working on implementing a means with Torizon Core Builder to allow you to apply the signatures without having to deal with a full Yocto build. So that is upcoming functionality. And when you get the slide, there's a lot of references here, including links to the GitHub pages. I won't leave that up, but you'll get those in the slides. And we would encourage you to get started with Torizon today. All the details here, Torizon.io is the way to go. And that said, now I think we have a few minutes left for questions. Let's see where we are. And Stefano, you are joining me. Very good. All right.
Yes, I'm here.
So let's see. We'll start with this first question. And this goes more to the BSP side of things rather than Torizon. What is the impact of secure boot with non-Toradex OTA mechanisms, things like Rauch OS tree? Well, obviously we use OS tree, but can the secure boot mechanism that we provide be used with something like Rauch? I don't know, Stefano, if you wanna handle that one.
I can answer. So first of all, I should say, let's start from the OS 3.1. That is what we use. Of course, it's compatible. Our update solution was just designed to support everything regarding secure boot. This means, to give you an example, if you flash something completely wrong, you send an update that it's signed with the wrong key. In our case, for example, it's implemented even a rollback, so you are not going to break a device. On all other update mechanism like Rauch at the end, I consider Rauch only a kind of client. So I really can't answer because I can't answer precisely. There is for sure required some work. It's not that it will work out of the box, but it's not that I can provide you really a true answer. I think that it's required some work to make it compatible, especially to make it sure that it's able to capture eventually and handle a situation where you send something wrong and you need to recover or something like that, or if the device will just shut it down during an update, etc. And as far as I know, Rauch don't support bootloader upgrade. Then probably I could be wrong, but they don't support bootloader update, and this is an issue for a secure boot system.
Yeah, I think they have something similar to our subsystem update feature, so you could implement that. But yeah, I think the basic answer is there's nothing technically precluding our secure boot from working with other systems. It's just a matter somebody's got to do the work to make it happen.
Yeah, Drew, just one last note, just to make it clear. As you probably already say, I want to just, let's say, remark a bit. The way of how we structured our Yocto environment, you can just create a basic Yocto image with all the security features enabled. This means that the image that is going to be generated will be a secure boot image where the bootloader will be signed, the fit image will be signed, the root file system will use DM Verity. That it's one of the most common way. But then to go up to implement updates, it's everything missing. So you need to implement it.
Yep. Okay, great. So next question. For app or Docker verification, would it be valid to put a public key into the OS signed by the private key from the bootloader and then have something in the OS verify that signature? I think that's essentially what we're doing. I mean, I suppose, Stefano, users that maybe wanted that container validation today could implement something themselves, but if they were unable to wait for us to get that out as a full product feature, is that a fair statement?
Exactly. So you could do it. We still, as you showed, Drew, in the slide, we are in the process to release this, to develop and release it. Actually, we are in the development phase. And yeah, you could do it if you add the key in the part of the root file system that is the one read-all, that is checked. You could continue the chain basically, because that's the concept of secure boot. But let me add one note: why still not ready? Because guys, you need to know there are some movement in the community. So there is Docker doing something, Podman doing something about this specific topic. So we decided to participate, understand where people is moving, just to not do something completely custom, and then be locked on something that probably no one will use. And we don't like this approach. Usually we really try to use a standard, very well tested thing. So that's why it's still not released.
Right. Okay, somebody made a comment, not really a question, but that app and Docker images can't be read-only because they do need to be updated in the field. And yes, that's true. Our secure boot implementation using Compose FS and FS Verity does not require read-only. That's a limitation of the DM Verity implementation, and so that should not be an issue. The fact that those files aren't read-only, and that's exactly what our protection is working against. I don't know, Stefan, if you have anything to add to that.
Completely true. I want to just add that even for configuration, it's the same. Configuration. Imagine you need to configure the IP or the Wi-Fi or whatever. The configuration is something that can be isolated and moved out from the secure world, let's say. And so it's something that you can definitely do in our system. It's pretty flexible. So, yep.
Yeah. Okay, so next question is about the difficulty or inability to use Easy Installer since it's not signed with the keys. I guess the question really is, how do we do that if we want to do an update to the bootloader or the basic OS with once the device goes to the customer? And I think the simple answer to that is you use the built-in update system. But I know, Stefano, you were mentioning there's some tooling provided, I guess, by NXP that can allow you to overwrite, for instance, the bootloader if it gets corrupted. That's a very manual process, but I don't know if you want to elaborate on that a little bit.
Yeah, just a couple of things. So, yeah, it's right. TEDSI is what we call Easy Installer internally, is not signed. So when you close the device, you can't use it because the system will not be able to boot it. Yeah. So we will do something on Easy Installer, not soon, but probably we will do something to simplify the recovery. But today, what you can do in a closed device is, let's imagine you flash something that is completely wrong. So you have the device that is kind of locked. What you can use is you can use just this tool provided by the chip vendors. Let me do an example with the NXP one. You can use these UUU tools to just replace the bootloader in the, on the device. But of course, this is really, it's not something really easy to use because you need to connect to a special port. I mean, it's something complex to do. That's why we really suggest to envision an update system that could handle updates and even failures with rollbacks. That's the solution that you should adopt. Then, of course, for testing purpose, for development, I think it's always useful to understand how to eventually recover this. But this is documented. So,
is there an authority to verify the process or any conformance standard? I don't think, in terms of conformance, I don't think Secure Boot is a standard or anything like that. It's just the general idea of that chain of trust where you're verifying the signatures, right? You mentioned the CRA. I suspect the CRA doesn't explicitly say you have to have Secure Boot. I suspect it says you need to have a means of verifying that authenticity and integrity. Exactly. And then how you implement that is really up to you. So I don't think in terms of a standard defining it, I don't think there is one. As far as authorities to verify the Secure Boot, I would imagine that would come back to penetration testers more than anything. I don't know if you've heard of anything, Stefano, that would.
Yeah, I have some argument here, because we could say it's a standard exactly like it's standard writing a Linux kernel module. Yeah, there is no standard at the end. Everyone can do what they want, but there is something that we could call standard, because, for example, where we store the key of in the bootloader was already designed by the guy of Secure Boot to do like that. Right. And the same way, for example, the fit image. First of all, the fit image, it's something not that we created. It's available, and we use it. The fit image put all together, Linux kernel, initramfs, device tree. And the way how the fit image check every component by integrity, it's already implemented. So in its way, it's a mechanism available in the system, in the kernel. So that there is this. It's not that we're implemented. So the answer is No, it's not standard, but it's a kind of standard. It's what it's mostly used in the world when we talk about secure boot. Probably what it's a bit strange, let's say strange here, like not really standard or not so common, is that for Torizon we used ComposeFS plus FS Verity, and looking around on the web, seems that no one still used that system. Not because it's bad, because I think it's a complex thing to do, and just a few people did. Also because the secure boot now is becoming a hot topic. Until the, I mean, if you consider a few years ago, people was just interested to secure the first part of the chain. Then what is way more popular is DM Verity. So just transform everything closed, everything read-only, and this is pretty popular. So probably someone could consider this more standard, but there is not really standard. The standard, as you say, Drew, it's about be able to provide a mechanism that allow to check authenticity and integrity. That's the only standard things.
Yeah. Okay. And so the follow up was, what about experts to validate it, or for certification purposes? I don't know of any. Certainly for some of the things like the medical or military, there might be more intense certification processes. I believe the CRA, at least initially, is probably all self-certified. I don't know that there's any official certification that's built in, but I'm certainly not the expert on that.
Yeah, I also don't know.
Let's see. So I think we've got most of these questions. There's a lot of closely related questions. Will a non-closed device load signed binaries? Yes, that's exactly what I was doing in the demo. It's only the case of a closed device that cannot load an unsigned binary. And then I guess the last question, what about using the Torizon Yocto layers? Would we recommend it on non-Toradex hardware? It's standard Yocto stuff, like you said, Stefano, right? I mean, it's not guaranteed to work right out of the box. There's work to be involved, but certainly we would love that, and we would love people to come into our open source community and help and contribute. I don't know if you want to talk a little bit about what contributions we might accept, especially in Meta-Toradex security, but I think there's definitely room for all of that.
Yeah, let's clarify a bit this, because I explained that we are open to third-party hardware, but there is something that I want to clarify. So if you use Torizon on our, or even BSP reference image on our hardware, all the features that we show today in this presentation are available out of the box. There is even easy installer and all the stuff, all the tooling and everything that you saw. What happened on third-party hardware? On third-party hardware, we work a bit, let's say, on demand. We have a standard unsigned version of Torizon that you could build. As today, we already support x86, Raspberry Pi, the Beagle Bone, Beagle Play. There are few you can check on the website. I don't want to, for sure I will miss someone. But they are not, for the moment, they are not still ready out of the box as our product. This doesn't mean that we cannot do it. So we are pretty happy to eventually receive contribution or eventually to do on demand. For example, we have some customers that have mixed fleet, and we did for them. So we supported even third-party hardware, and that is something that we could do, and we can. You can contact us if you have interest on any third-party hardware. Could be whatever chip vendor, and we can eventually consider that.
Yeah. All right. Well, very good. That's the end of the questions. I want to thank everyone for your time in attending here. If you do have any further questions, feel free to reach out. We're pretty easy to find. And with that, Stefano, I'll give you the last word.
Thank you so much, everyone, to be here, and see you in the next webinar. See you soon. Bye-bye.